Cool. So now we're recording. All right. So hopefully you all, when you walked in, picked up a hard copy of the STEAM tables. If you didn't, you can pick one up on the way out. You won't need it in class. I think it's just, for those of you that have virtual books, it's a real pain to be scrolling through virtual STEAM tables. So there's obviously, there is virtual stuff on Moodle for all the tables, but I think a hard copy is nice. We use the water mostly. We'll use some stuff that's like carbon dioxide or methane or some of those other substances, but mostly water. So we'll have a hard copy of the water tables. All right. So one of the things that I think you'll find is that the math in this class is pretty easy. I think it is, and I think you will think the actual math that we're doing, most of it is stuff that like 10th grade you would be fine with. The stuff that's not, that's like actually calculus, will be the stuff that you prayed for on your calculus exam. Right? So we're not doing anything that's super crazy. Right? This isn't like, there are some engineering courses where part of the course, part of engineering is learning how to take complicated math and fit it to the real world and help it answer questions about the real world with really complicated math. That's not what this course is. This is more talking about kind of the concepts and stuff in, I guess, more of a concrete way with less complicated math behind it. We'll do some calculus in kind of the second half of the semester. But then what the challenge is figuring out how to approach problems and how to look at them and how to think about them. That's more what we'll focus on in this class. So how do we kind of conceptualize and think about thermodynamics with kind of lighter on the math than maybe some of your courses will be. So this is one problem. Just spend the next 5 minutes thinking about this. Try to write down step by step how you would go about actually figuring out the answer. And I think one of the things too is, how would you go about determining the final state? So we have a tank A and tank B. There's a valve in between initially. We open the valve, things happen. We get to some final state. What would that look like and how would we figure it out? And what information would we need to be able to do that? So spend like, I don't know, we'll say maybe even just 3 minutes, and then we'll come back together as a class and talk through what our solution plan is. Okay, so let's come back together. What would be, if anybody wants to share, what's your plan of attack, at least first steps, for figuring out what the final state might be? And how would you do that?
Quick question, can we assume that tank B also has a 1 meter cube? I don't know if it matters at this point. But could you assume that it's also 1 meter cube? Okay.
So never assume. You've heard the joke about what happens when you assume, right? No? I probably can't say it recorded. For those of you that have heard it. Yeah, Jack?
Can you use P and T and tank B to find the specific volume and multiply the mass to find the total volume?
Yeah, so if you find, exactly. So instead of, we do need to find, you're exactly right, we need to find the volume of tank B. So we can use pressure and temperature to find the specific volume of B, and then use that to find the total volume of B. So I'll label that maybe our first step. Yeah. So that gives us now the total mass that's in B and the total volume of tank B. So we could do a similar thing in tank A to find the total mass of tank A. Right, so we can use these two and find the mass of A from, right, so it would be from the, I said write in words, but I'm kind of writing in math, I guess. So find mass of A, because mass equals volume divided by specific volume. So that would give us the total mass of A, the mass of B, the volume of A, and the volume of B. So then we would know, so this would be, I guess, step 2. Step 3 would be find mass final write that a little bit better, and the final volume, and then use that to find the final specific volume. So ultimately what we're asking, if we're trying to find the final state, we need to find 2 independent properties of it, right? One of those can be specific volume. So from the total mass and the total volume, we can find the specific volume to find specific volume. Let me write that a little bit better. Okay, and the final specific volume, right? The reason that that's good to be able to find is that's not going to depend on, right? What the problem says is the valve is opened, and the tanks are allowed to come to a final uniform state. We're not told anything about what that final, how that happens. It happens. But it doesn't matter how it happens. It doesn't matter if like things are heated up or cooled down or happen fast or happen slow or however it happens, it happens. The process doesn't matter because the total mass is going to be still the total mass, and the total volume is still going to be the total volume. The pressure and temperature, we don't actually know enough information about the process to be able to know what the final temperature or what the final pressure would be. We're going to spend quite a bit of this course kind of thinking through processes. Like how do you get from point 1 to point 2, from an initial state to a final state? What is the path that you take? Is is there heat flow involved? Is there work involved? Is there, does it happen fast or does it happen slow? How does it actually happen? And to be able to really solve this problem and to actually figure out what the final state is, we would need to know something about how it actually happens, what that process looks like. So we don't have enough information just from this problem statement to be able to figure out what the final state is. We would need at least one more piece of information. So we'll spend a little bit of time. This is kind of like, describe this problem as kind of steam tables, kind of steam tables 2.0. Where this will be the participation problem for the week. We'll be figuring out for, okay, now given a final temperature, then that you know something about the process, and then you can figure out what actually happened. But just with this information, we wouldn't know. But I think that sets us up. A lot of this class is going to be talking about how would we figure out, like, what is the pathway that we take to get from an initial state to a final state, because that matters in a lot of cases. In all cases, it matters. Okay, the next thing I want to just talk briefly about is interpolation, because we're going to be, you've watched videos, you've done interpolation before, so I'm not going to spend too much time on this point, but I just want to show graphically again what we're doing, just to kind of, I guess, reiterate the point. So this is data from table B.1.3. Which is for steam. So this is steam pressure versus specific volume. We have these data points. When we're interpolating, again, I just kind of zoomed in on a subset. When we're interpolating, what we're saying is that this is what the data looks like, right? We're just drawing straight lines between all of the data points. That's obviously not really what is happening, right? The data is really a curve. So depending on where we are, our interpolated values are always going to be different from what the actual value is at that temperature. Right? Sometimes, like the case over here, the interpolated value and the real value might be really close together. If we were somewhere over here, the interpolated value and the real value, right, there's a difference of a fair amount between the interpolated value and the real value. We're going to kind of pretend that interpolated values are the real values, just because most of the time we're not interested in, when we're doing like steam tables and interpolation, the exact answer doesn't matter that much. We're more interested in like the process and how to think about it. We're not calculating the performance of a real system that it matters if we're off by 5%. If we're off by 5% and we're all off by 5%, that's okay. And obviously, you wouldn't do interpolation like this to get an exact answer. We'll learn how we would do stuff like that to get a better answer later in the course. But the other thing to note is, right, if we're interpolating, you always want to interpolate between the two closest together points. So if you tried to find, say, a point here at 250, and you interpolate between those two, like this point and this point, you get a pretty close answer. But if you interpolate between those 2 points, you could be like way up there. So you could be off by a lot. So you always want to be interpolating between the two closest points. And you don't want to be extrapolating, because then you could, right, if you're extrapolating from these 2 points, you could guess somewhere down there. So interpolating the 2 points closest to the one that you're actually looking for. And again, we're going to just know that, be aware that obviously this isn't like giving you an exact answer, especially when values are changing relatively quickly. We're going to kind of pretend that it is, but know that it's actually not. Okay. What we talked about last week was kind of a crash course intro to thermo, and we had this, I don't know, kind of silly thought problem where we looked at, what happens when you mix water at 2 different temperatures. And you guys guessed correctly what would happen. We said, really, like, we can think of that simple problem as like the assumptions that we made to figure it out are really the first 2 laws of thermodynamics. The first law being conservation of energy. Right? When we took hot water and cold water and mixed them, we got an average temperature because the heat didn't just disappear. And similarly, the hot one always got colder and the cold thing got hotter because heat only flows one way. Right? Those were our 2 laws of thermo. We'll set aside the second law for a little while. We'll come back to it again next week, and then we'll keep coming back to it again basically every class period following, because that's a fun one to really start to dive into. But we'll start this week with kind of a better definition of the first law and how do we actually use it. So the first law, that's kind of small. So the first law of thermo, the definition that I'll give is, it feels just like conservation of mass. Energy cannot be created or destroyed. Conservation of mass. But then this is the fun part. I apologize for my handwriting. My handwriting is not perfect in the best of cases. It's just like trying to write on a tablet. I'll try that and see if it works better. So energy cannot be created or destroyed. It can change forms. It can change from heat to mechanical energy. It can change from mechanical energy to electrical energy, or electrical energy to chemical energy. It can change from one form to another, nuclear energy into heat. All of these different changes are possible, but as a whole, energy is conserved, just like mass is conserved. So this implies that, right, in 150, use conservation of mass to do mass balances. You also did a little bit with energy balances like this. But this implies that we can do balances. Right? If it can't be created or destroyed, then we just have to track where it goes. And whether it changes from one form into another and how everything works. We just have to track it. And we can track it because it doesn't just disappear or appear magically. So one way, the first way that we'll talk about, kind of the framework that we'll think about energy balances, is a control volume. The abbreviation that I'll use almost exclusively is a CV. And what a control volume is some arbitrary volume, right? It's some arbitrary physical part of space that we happen to be looking at because we're interested in it for some reason. And we can have mass flow in and out of that control volume, right? Think of it, to put a little bit more concrete thing, we'll talk about this in a second, doing a control volume on a pump. And we could have mass, like water could flow into the pump and water can flow out of the pump, and the amount that flows in has to equal to the amount that flows out because of conservation of mass. The same thing with energy. So we can have mass flow in and we can have energy. And we can have energy flow out. And we're going to use this as a framework to be able to track where energy goes, because the amount that comes in has to be the same as the amount that goes out. Okay, so here's a this is the ugliest pump I've ever drawn, but that's a pump. Okay, so in this pump we have an inlet. We'll call the inlet the inside 1, the outlet side 2. We have something, we'll call it water, could be anything. We have water flowing in one side and out the other. So we can describe that flow rate, that's a mass flow rate. So water's flowing in side 1 with a flow rate m.1. Right, some number of, say, kilograms per second or pounds per hour or whatever our units happen to be. It's flowing in the one side and out the other side. We have underneath our pump that's a campfire. Somebody lit a campfire underneath our pump. And we, as engineers, want to look at the performance of that pump. We want to look at what's happening with energy in that system. So we're going to look at a control volume, which kind of selects out just that piece of equipment. Okay, I lost it. Where did we go? Okay, so this is our pump. Okay, so we can do it. The first step that we're always going to have to do is a mass balance. In a lot of cases like this, the mass balance is almost silly because it's so easy. We're never going to get to really complicated mass balances like you did in 150, but we'll have systems where there's like 1 inlet and 2 outlets maybe, or 2 inlets and 1 outlet. We're not going to get into anything super wild in this class, although we could. It just kind of clouds things, makes things a little foggier. So, but we always have to start with a mass balance. So conservation of mass, we can write that as the sum of all the mass flow rate out minus the sum of our mass flow rate in must be equal to 0. This is conservation of mass at steady state. And I'll underline steady state because this is something that's not changing with time. Obviously, if the pump is empty of water and we just turn it on, there's going to be some amount of time where water's flowing in one side and not out the other, right? Like it takes a little bit to get going. Maybe it's only a second, but it takes a little bit before water comes in one side and goes out the other because it didn't have water inside before, so there's going to be some accumulation. We're not going to do things that are changing with time in this course. Again, you can. That's certainly part of thermodynamics, but we're not going to get involved in those weeds. We're going to stay in kind of the simpler case where things are not changing with time. So for us, this will be our mass balance. We can just look at in equals out. Same thing with our energy balance. Okay, our energy balance is going to be the exact same. So the sum of the energy out minus the sum of the energy in is equal to 0. Now the difference is so I'll write again at steady state. So this is the first law expressed now mathematically. The difference between energy and mass is that energy can come in different forms. So if we think of just this problem here of the pump, what different forms of energy are going in or out of our control volume?
Is the heat and the fire?
Yeah, so form of energy number one is thermal energy or heat. We'll call it heat. To or from the surroundings. Our variable for that will be Q. And we'll use the variables that we'll use in this class are like Q dot, capital Q, and lowercase q. Right, this, just to make a note, this means the rate. So like a per second. Well, I'll just write what the units would be, like kilojoules per second or joules per second. That's how fast is that? That's a power, actually. That will be the dot. The dot means rate. Capital Q, this is total, which would be, right, something like a joule, the total amount of energy. And this is specific, which would be like joules per kilogram. And that's going to be true. The same, we'll use the same convention for all of our variables. So the rate with the dot, the total amount, or the specific amount. Okay, so that's one of them, heat to and from the surroundings. Any other forms of energy that are present and we would need to account for in this system? There are 6, but we have 1. Yeah, Dan. Kinetic energy, yep. So we'll use the variable E sub k, energy kinetic, just to be kind of in line with how our book writes it, kinetic energy. Any other kinds of energy that are present in this example that we would need to account for? There's still 4 more. 3 are reasonably easy. 1 you're never going to get.
Mechanical? Like
Yeah.
I'm actually doing the work.
Yeah, so there's presumably like a blade or something inside the pump that's spinning and moving, which is doing the actual pumping and imparting some energy to the fluid to pump it. So that would be what we call work. Say 2 types, see below. So we'll get back to work in a second, right? Work is a force applied over a distance. One way that can happen is through like the movement of some mechanical thing. There's another type, which we'll talk more about work because that's kind of a weird one. Is there any, so a couple more. Just to go quickly, right? We come in here at the bottom at 1 and we leave out the top at 2. What kind of energy changed? We go in low and come out high. We change in potential energy. So we're going to have potential energy. Okay, any other kind of energy? There's one more. The actual like thermal energy of the fluid itself, right? So a fluid is coming in, say it's water, that has some temperature and pressure, and it comes with its own energy. Does anybody remember what we call that? internal energy. Right, this is the, I guess a better word would be thermal. So this is the thermal energy. The thermal energy of matter. We give that the variable U. And because U is a hard one to differentiate capitals and lowercase, I'll use like a U without a tail and serif set on it. That'll be our uppercase U, and if it has a tail, that's a lowercase u. And I will try my hardest to be consistent on that. Okay, so these are the types of energies. The last one, right, to talk a little more about is two types of work. Right, so we'll expand a little bit on that. The first type of work is what Jack said was what we'll call shaft work. Which is mechanical work from like a moving thing. Or moving machinery. Like there's a part of the pump that's actually physically moving, and that's imparting extra energy into our system, doing mechanical work. The second kind of work, yikes. I don't know why it does that. Okay, the second kind of work is called flow work. And this is the work required to, and I'll just give this, to push the fluid in or out of our control volume. So work is, right, work is a force times a distance. So we can think about it when we have like a moving mechanical part, it's easy to picture, right? That like blade pushes on the fluid over some distance work. If you think of what happens to the fluid, right? There's some amount of fluid that's, and I'll try to do this without gumming up my picture too much, but there's some fluid that's like right here, just outside of our control volume. When that moves, it has to move from just outside the control volume and get pushed to inside the control volume. So it gets pushed across that boundary. When that happens, right, a force was applied and it moved. So a force was applied over a distance. So there's a work associated with the movement of that fluid. So we can write, we're not going to derive this in detail, but hopefully this gives you another, right, another thing, right? This is, we're talking about energy. So as this piece of fluid is pushed across the boundary, you think of it, the surroundings, which is just anything that's not inside of our control volume, the surroundings pushed it inside. Or if something is leaving our control volume, then the control volume pushed to get it outside. So it's going to happen on both sides, whether something is going in or leaving. Right, work is a force times a distance. So the work, the flow work, is going to equal a force times a distance over time. Right, if we do the little dot, because that means a rate, which is a per time. Distance over time is velocity. So this will be a force times a velocity. We can divide a force by an area. So that would be a pressure. Multiply a velocity times an area, and we get a volumetric flow rate. Again, you don't need to know the definition exactly, but just to see a little bit where this comes from, that this really is, this is a work, just a force times a distance. So our our flow work per unit mass is pressure times specific volume. So every time that we have we scroll up, I'll come back down if you didn't write everything, but every time we have a system like this, where we have a control volume and we have something like going into our control volume or leaving our control volume, there's always going to be this pressure volume term because it had to move. Likewise, there's always going to be an internal energy term because it has some finite temperature. So if there's a thing that moves in or out of our control volume, it always has these two things. It has flow work and internal energy. So just kind of for simplicity, we combine these and we define what we call enthalpy. Which we give the variable h. And we define enthalpy, so capital H or lowercase or h dot, whatever our specific units happen to be. We define enthalpy. H is defined as, so this means the little 3 equals arrow means defined. So H is defined as U plus pressure times specific volume. Right, this is our H is the enthalpy, U is internal energy, and this PV term is flow work. What it really is, so get a different color. So H just kind of for a conceptual definition. So it's the energy that a flowing mass carries with it, both as its heat and like because of its movement. Yeah, Abby.
So the lowercase h would be the specific enthalpy in that equation, or are they the same thing?
The lowercase h would be specific.
Okay.
The capital H would be the total amount of enthalpy. Say in like, how much enthalpy does 10 kilograms of water have? That would be capital H. Water is flowing at 1 kilogram per second. The enthalpy rate would be H dot. How much enthalpy per kilogram does water have in this state? That would be lowercase h. So the lowercase letters are going to be the ones that you find in the steam tables.
So you can't use that equation to find the uppercase h, or can you still use that?
So you'd use to find uppercase h, right? Uppercase h equals m lowercase h.
Okay.
So you could rewrite, so capital H equals capital U plus P capital V.
Okay.
And you could do, if you wanted to, or capital H dot equals capital U dot plus P capital V dot. Right, all of these equations are the same. You're just changing basically like how you're dealing with mass. Okay, so I know we're getting to the end of class, but I need to get through this next part, otherwise you won't be able to jump into the homework, or it won't make sense when you do. So if you can give me a couple more minutes, that would be appreciated. So, right, what we're trying to do, if we scroll back up, what are we trying to do? We're trying to do this energy balance, energy out minus energy in. So now we have a number of different energy terms that we have to deal with. We can deal with kind of each of them separately. So this is our, right, a little bit bigger. Our control volume energy balance, we can write a general energy balance for our control volume. Okay, this would be our general energy balance for a control volume. Right, so just to go through what these terms are, this would be the change in enthalpy, which is, right, this combination of, like, it's the total energy that the fluid carries with it, both thermal energy and kind of this mechanical flow work energy. Kinetic energy, how fast is the fluid moving? If it comes in fast and leaves slow, there's going to be a change in kinetic energy, change in potential energy. And then the other side is Q minus W, heat minus work. This is specifically what we would call shaft work. Like, it's, are there moving parts? So a lot of the challenge, this will be like always your starting point. If you're doing an energy balance on a control volume with that framework, like, this is the starting point. And then you have to ask yourself, which of these terms are important? Right, if you come in and you leave and the height difference is only 3 millimeters, the change in potential energy is probably not relevant to the system. There are probably like big changes in some other kind of energy and just that little teeny tiny bit, which is going to get, you know, dismissed by rounding error. So they won't all be important in every system, but this is like the starting point, and then we simplify down from there. Just a couple notes on the equation itself. Right, for the left-hand side of the equation, the delta means out minus in. So all of those deltas, right, delta kinetic energy, that means the kinetic energy 1/2 mv squared, the kinetic energy that it's leaving with, minus the kinetic energy that it brought in. This is just to get all of your sign error, right? This is like energy balance is accounting, so you have to make sure that your positives and negatives are all correct so that you get the right answer. So for accounting, we do out minus in. Right, as we said before, this dot symbol means rate. But we could just as easily write this. Typically for a control volume, we're talking about, right, we're using a control volume because things are flowing in and flowing out. So that's why we would write it this way. We could write the same equation where we divided by mass flow rate and we had like specific enthalpy and specific kinetic energy and specific potential energy. So we can go back and forth between those by mass flow rate. Right. So just as an example, so equals mass flow rate times specific. So we can go back and forth between these two. We'll always use that convention though, where like lowercase means specific, uppercase means total, uppercase with a dot means total rate. And then the last thing to note, the right-hand side. So note the sign on the right-hand side, Q minus W. So that minus sign, we have to, right, the reason that this energy balance all works out is because of how we're tracking where energy is going. We're saying that the total amount of energy in equals the total amount of energy out. We just have to figure out like which way do we define as in and which way is out. So if we go back up to our little pump problem, we had heat energy going into the system. Now is that positive or is it negative? We can pick, we just have to pick and be consistent. Same thing for a pump, we plug a pump into the wall. So we're putting work into the system. Should that be positive or should that be negative? Doesn't really matter, we just have to pick and be consistent and then figure out our signs from there. So the sign convention that we use, that's typically used in thermo, is right, thermo's born out of the steam engine. That's when people were first writing down these equations. So they were thinking about steam engines. So think about a steam engine. What does a steam engine, what does a steam engine do? You put heat in and you get work out. So we define both of those things as positive. Again, it's just by convention. So heat in is positive. And work out, getting work out is positive. So again, if we go back up to our pump, we have this campfire, so we're putting heat into the system, so that would be the amount of heat that's going from the fire into the pump, that's a positive. We would put a positive in our equation. We're putting work into the system because we have our pump plugged into the wall. That's going to be a negative. So because we're putting work in. So that's going to be a negative value that will plug into our equation. So for that, we would plug in, here in Q, we would plug in a positive, say like positive 10, minus negative 5 kilowatts, or whatever the work of that pump would be. So that's the only, right, I think if you go back to a steam engine, think about a steam engine, that tells you what positive should be. And then you just have to make sure you plug in a positive if heat's going in or work's coming out. There are a couple example problems on Moodle. So that's like the second half of this lecture. There are 3 of them. You all have done some stuff like this in 150. So I'd say for sure watch the first of the example problems. There are 2 other example problems, which I kind of have put on as optional. You don't have to watch the video. So for the 2 other example problems, I have like my note outline if you want to watch the video and follow along, or I just have my final like filled out notes if you want to just pull up those and scan through them real quick. Do however makes you happy. But hopefully those will give you a little bit more practice, get us back in the groove. I know you've done some of this in 150, but this will get us back in the groove of thinking about energy balances and how to account for all of these things for different types of systems. So that is all for today for the in-person section of the course. So there are a couple of those videos on, I guess on YouTube, on Moodle. Feel free to watch those. Hopefully this little like Moodle checklist thing, you find that useful. If you have any other comments, I'd love to hear them. Yeah.
The quiz is due today, right?
The quiz is due today, so take the quiz sometime today. I'll probably sometime tonight go and look through and see if who hasn't taken it yet and maybe shoot you out an email just as a reminder. But it's like a 15-minute quiz. I guess the last note about the quiz, you'll get a grade that will get, right after you take it. The grading on Moodle is super hard from my end. Like, I just am kind of making stuff up. So if you get it right, you'll know that you get it right. If you get it wrong, don't really worry about the score that Moodle gives you. I promise I will go back in and look at what you actually wrote down and give you a real score. And that will be true for all of our Moodle stuff, whether it's the quizzes or the participation assignments. Both of them, I'll go back in and correct the scores. I'll wait until after, so I'll probably, I don't know when I'll do that. It'll probably be next week for the quiz, but expect your score. Your score won't go down. But if Moodle like spits out a 7 or something like that, you probably really got like a 12 or a 13 or something like that. So kind of hold off judgment on the score that Moodle spits back, because it's hard for me to, like, sometimes I can see from what you wrote down, like what you were thinking and where you were looking, and it was close, but not quite there, but the number is way off. And unless I go through and program in every possible mistake that you could have made, Moodle doesn't know how to handle that. But it's easier for me just to go back and like check it after it's done. So, so don't worry too much about the grade that Moodle spits out right away. That's probably not going to be your final grade unless it's a 15. I think that's it. Again, sorry. So I'm struggling.
How many?
It's 2. I'm struggling with the whole timing thing here. It's hard to figure out exactly like timing my lecture, and I have to get through like a certain set of stuff. So again, bear with me as I try to figure that out. I'll try to for sure keep it within an hour, but I'll try to be 50 minutes and respect your time that way. The other change from previous weeks, I guess I can stop recording here in a second, but the other change from previous weeks is because we're all here already, and I'm here already and we have this room, we'll just use this as a chance to run over like office hours type questions. So if you want to leave, if you feel like you're good on homework and everything, you're free to leave. Otherwise, if you have any questions, just hang around and we can chat about any of that. So, and that's true for you virtual people as well. You can hang around virtually and we can chat too. So with that, I will stop the recording and everybody have a good week.